Good afternoon, ladies and gentlemen. Welcome here at the Technical Forum at the group exhibit Hydrogen, Fuel Cells and Batteries, this year here at Hanover Fair in the year of 2015. This afternoon's topic is hydrogen production and energy storage. Every 15 minutes you will hear interesting presentation concerning the hydrogen industry. Now I would like to present to you the next topic, hydrogen in a sustainable energy system, a combination of storage medium and fuel. For that, please welcome with me on stage Deputy Chairperson of the Deutscher Wasserstoff und Brennstoffzellen Verband, DWV, Dr. Johannes Töpler. Big hands, please.
Okay, thank you very much for the kind introduction. Ladies and gentlemen, when we want to discuss about hydrogen in a sustainable energy system, let us start with a consideration of our actual energy system. You see here our basic energy system today is mainly influenced by oil, natural gas and coal. The availability of these systems are decreasing, and in future we will have wind, photovoltaic, solar, thermal energy, biomass, geothermal heat, and so on. And this is a consideration of World Energy Outlook in 2005, and that is what is to be expected. And if I present you this figure in another color, you will see here the conventional energies in blue, the renewable ones in green, and a special situation is biomass in brown. And we see that the basic energy systems today can store energy. The energy is stored in coal, natural gas and oil. That means we have a fuel-based system. And if we want to make electricity, we have to convert it with a low efficiency in a power station. And in future, when we will have solar thermal energy, photovoltaics, wind power, we will start with a technical energy system by electricity. The first energy by converting natural energy for technical application is electricity. That means in future we will have electricity and we have to convert it for other applications to fuel. That's a strategic change in the strategy of energy application. And now these energy are not constantly available and not on demand. These energies are fluctuating, and what does this mean is shown here in this figure. That's the wind power in 10 days of March in 2007 in the E.ON electrical grid. And you see here the fluctuations. And in Germany we have the legal situation that we have to increase wind power by a factor of 3. This is to be expected. That means with the same meteorological conditions, the same curve will be in 2020, this blue curve. And now you see here, for example, that we have in this part a supply which cannot be satisfy the demand. The supply is here, the demand is here. And we have other days where the supply outreaches the demand by far. And what we have to do is to store it so that in times of low supply we have enough energy. And this storage system can be shown like here. It's one model that wind energy is converted to electricity and used in households and industry. And the surplus in those days, when we have more energy than can be used, we can make electricity, we can make hydrogen by electrolysis. We can use this in fuel stations as fuel, hydrogen as fuel for mobility. We can store it in big caverns. We can use hydrogen from these caverns, and we can use hydrogen for households, for house energy supply, and afterwards we can reuse it for electricity by turbines, fuel cell and via electric grid as electricity again in industry and households. With this storage system, we can make the energy supply constant or on demand. For the case of hydrogen use in households, there is another additional way with methanization, the so-called power to gas via methanization. This can be done in some time in between when we want to use the natural gas network. There are some other possibilities to store energy, and this is shown here. For example, pumping storage systems. The energy is mainly limited up to 5 gigawatt hours. For example, for the biggest system in Germany, in Goldistan, it's 5 kilowatt hours. That means round about 5 gigawatt, round about 1 gigawatt power for around about 5 hours. Or another possibility is advanced compressed air energy system up to round about 100 bars with an energy capacity of 23 gigawatt hours. This is this blue square. And if we want to use hydrogen with a very, very high energy density measured by volume, we can store round about 1.3 terawatt hours with turbines up to 3 gigawatt. That means hydrogen is chemical energy carrier, has a very, very high capacity to store energy, big amounts of energy for a long time. And this is shown once more here in this figure. Here you see the hydrogen content per volume, the density per volume, with 100%, round about 280 kilowatt hours per cubic meter. If you reduce this by the efficiency of electrolysis and fuel cell, you have still round about 170 kilowatt hours per cubic meter. In this relation, the adiabatic compressed air energy system is round about 2.4, and the pumped hydro system round about 0.7 kilowatt hours per cubic meters. That means the hydrogen density is very, very high, and that's a physical reason because big amounts of energy can be bound or stored in big caverns with hydrogen by chemical reasons. The consequence, in a summary, hydrogen makes renewable primary energies ready for basic supply. It's very, very important to have a guarantee of basic supply for the energy distribution. And by this way, the hydrogen transition is affordable because the stored hydrogen can be used for a lot of applications as fuel additionally. And by this double or triple use, the whole system becomes affordable. And now let me say some words for hydrogen as fuel. For example, in motor cars, this is done especially in fuel cells, not in combustion engines due to the efficiency. A fuel cell has an efficiency of round about 52%. For traffic application in the normalized cycles, and the relation to conventional fuels is round about 22% for the same cycle. This is a fuel cell system, the stack, the auxiliary units, for example, the pumps and compressors. This is the cooling system, and this is a propulsion engine, an electric engine. And here you see the hydrogen storage system is a gaseous storage system with 700 bars. And here is an additional battery. This battery is used for the reuse of braking energy and for other purposes. I will show it later. And here is one possible description of a car. It's a Daimler B-Class. Here is the fuel cell system in the double bottom, and here is the auxiliary units and the drive, and at the back the battery. And this car like this was tested by a turn around the world in 125 days with round about 30,000 kilometers. And Daimler has announced the serial production in 2017. And you can see here today at this fair the first serial motor car from Toyota, and you can drive with it. The start of serial production of fuel cell cars has begun. And now let me say some words with respect to electric propulsion. We can do it in two ways, by batteries alone or in a battery fuel cell storage system. And let me tell you the difference. The efficiency of batteries is very high, higher than fuel cells. But the amount of stored energy is limited, and this has a physical reason. If we want to use gasoline or diesel, this is a principal chemical formula for gasoline and diesel. You have to take this with you in a car, and the oxygen is coming from air, and the combustion products like carbon dioxide or water vapor is given to atmosphere, and you have to take with you only this part. In the case of hydrogen, you have to take with you only the hydrogen. Oxygen is coming from air and water vapor is given to air. That means that you have only to transport hydrogen. In the case of a battery, you have a complete molecule, for example, in a lithium battery with lithium carbonate, with carbon, and with lithium at the cathode. In the anode, you have a big molecule of lithium manganate, and you have a lot of molecules only for a single electron. And if you want to enlarge the range, then you need for a double range a doubled tank in the case of conventional fuels, a doubled tank in the case of hydrogen, and a doubled battery like this. And therefore, that's the reason that by limited weight, you have always a limited range of battery-driven cars. In the case of hydrogen, it's somehow better. We have today hydrogen cars in the way shown with around about 500 kilometers range. And now let me tell some words about the combination of heat and propulsion energy in a car. In winter, you want to heat your car, and you can do it with hydrogen and fuel cell in a very good way without any reduction of range. If you have a battery and you have to heat, then you have a reduction of range. If you have a fuel cell with hydrogen, you can have an intelligent steering of your fuel. If you start your car with an empty battery, you can start the fuel cell before starting the car. And with this fuel cell, you can heat your car, and you can store the energy, the electric energy, in the empty battery. And you can preheat your car without any reduction of range. And when you start, you drive with electricity from battery and fuel cells in the same time. And if you are at your goal, you should take aware that the battery is empty again and you can restart. That means you can drive with the waste heat of fuel cell even before starting, and therefore you have no reduction of range by heating the car. And there was let me tell something about the advantages for different applications. There was a very big study, the so-called coalition study, with a motor car manufacturer, with a gasoline fueling station responsible people, and they have calculated where are the advantages for which ranges of cars. And you see here the battery vehicles, plug-in vehicles have mainly advantages in compact class vehicles and low ranges. In this case, when you drive only 100 kilometers between two fillings, then cars in this range has advantages. If you want to drive long ranges or you have bigger cars, this area of car application is very comfortable with fuel cell hybridized cars. This figure doesn't say anything about the number of cars. If a lot of people decide to use the cars only for small ranges, and small cars are fine for them, then here in this triangle can be a lot of cars. But these applications show where are the advantages by high efficiencies from batteries or long storage possibilities or huge storage possibilities for long-range cars. And now sometimes there are some discussions about biomass. And if you look, for example, biomass, biodiesel from raps methylene ester, you need a lot of area of hectares for growing up these materials. And by this way, you can drive around about 3 passenger cars from the result of 1 hectare. And if you make, for example, compressed hydrogen from short rotation forestry, you can ride round about 9 cars from 1 hectare result of biomass. And if you use hydrogen from biomass, if you take hydrogen, compressed hydrogen from photovoltaics, you have 1 hectare photovoltaics, you can ride round about 70 cars, and in the case of wind energy, round about 18. I will say by this that you need for biomass sometime a lot of area. And if this area is agricultured, then in this case you have a competition of food or fuel, and you have to be very careful with this. But on the other hand, we will have biomass from waste biomass. And then it is a question, what can we do with it? And waste biomass is always diesel or ethanol, and it has to be converted in an internal combustion engine. And the efficiency has always this shape. In the case of diesel at high loads, it's a little bit higher. It's a physical question of the so-called Carnot process. It's a thermodynamical process, and always the efficiency has this shape. In the case of a fuel cell and of a fuel cell system, you have an efficiency curve, a characteristic curve like this, and a passenger car is generally operated in round about 15% of maximum load. That means you have, in the case of a passenger car and in the case of an urban bus, you have always a stop-and-go operation at low load, and here the efficiency is much higher than a conventional internal combustion engine. That means if you have biomass and you use it in internal combustion engines, the best way is to do it with vehicles which are operated a lot of time at high load. That means airplanes, ships, or big trucks at long ranges. In this case, biomass has high efficiency, which can be compared, for example, with fuel cells. And another remark is, we have very often the discussion that if we have a surplus of wind energy, there is no cost. If this doesn't cost anything, then the efficiency doesn't matter so much. And here you have the efficiency steps of a surplus of energy. The first step is to make electricity from via electrolysis with an efficiency loss of 30%. Then in both cases using hydrogen or methanization. That's a path of power to gas with including methanization. Then you have in both cases efficiency loss of compression and so on for hydrogen, and for methanization it's quite similar. And at the end we have the high efficiency of fuel cell and the very low efficiency for synthetic natural gas in a diesel or in a auto engine. And here are the efficiency of the whole change from round about 22 in this case to 12 in this case and 29 in the case of wind. And the argument is, if this costs nothing, it doesn't matter what's the efficiency here. But if you look a little bit more careful and you say, it's the important is the energy which I need at the end, and you recalculate, this is normalized to 1, and if you recalculate to the early beginning of the energy conversion, you need here systems which are around about a factor of more than 2 bigger, and this costs a lot of invest energy. And therefore, it's very, very important how the efficiencies of the whole systems are. And the efficiency of the hydrogen chain is always very high due to the high efficiency of the fuel cell. And that's a very important argumentation. And if you want to calculate it yourself, there is an internet possibility by this internet address. This is presented by Daimler with some research institute, where for all energy paths of new renewable energies, the efficiency and the carbon dioxide emissions for all paths can be calculated by yourself if you go on this address, and then you will be guided to the whole system. And this application of hydrogen and fuel is not only limited on traffic on streets, but even, for example, in ships, for new applications in airplanes, at auxiliary power unit, and so on. The consequence is that hydrogen introduces renewable energies into mobility. Hydrogen enables electric vehicles to reach long distances, and hydrogen makes mobility carbon dioxide free. That's the main sentences. And now I thank you for your attention. And if you want to have more information, here is the internet page of our Hydrogen Association. Okay.
Thank you very much, Dr. Johannes Töpler from the DWV. There is a question from the audience. I will take this question.
My name is Wojciech Gis. I am from Motor Transport Institute from Poland. And my question is following. And we have seen that CO2 emission in aspect use of hydrogen is relatively low. This is true, but not. Which situation will be in life of a cycle in aspect produced from source to wheel, hydrogen, for example?
Okay, it was from source to wheel. I had shown from the early beginning of wind energy till the wheel at the car. It was an overall efficiency over the whole path.
Naturally, yes, but that means that we have energy from renewable sources. But yes, in Poland we have a small problem because we produce energy generally from coal. What we must do in this aspect?
Okay. It depends on the efficiency, for example, to produce hydrogen from coal. It can be if this effect is, or if this efficiency is not so low, then the efficiency of fuel cell compensate and overcompensate this, so that at the end the fuel cell is still better. But the advantage is very, very small. And sometimes if the efficiency from coal to hydrogen is very low, then it cannot compensate, then other fuels can be better, but the reason is the coal. And you have a lot of energy losses, by the way, from coal to liquid fuels. You cannot drive a car with coal, maybe a locomotive, but not a passenger car. And therefore it's a question of these processes. But the high efficiency of the end is guaranteed always.
Thank you very much.
Okay.
Thank you. Is there any other question from the audience at this time?
Thank you very much. Gustav Grob. I founded once the ISO Committee for Hydrogen, so I was an enthusiast of hydrogen. But I learned from the pioneer of hydrogen, Professor Bockris, that methanol is a liquid hydrogen. It's much more practical, much more economical, and Nobel Prize laureate George Olah has written a book about it, that methanol is a much more economic fuel. Why didn't you mention it?
Okay, hydrogen, for this purpose, hydrogen was very intensively investigated by Daimler in the 90s. And the reason is that it's very, very difficult to reform methanol on board of a car. It's very difficult, and the cold start is nearly impossible. You have to warm up a cold reformer system. It needs a lot of time. It needs a lot of energy. And Daimler was the only car manufacturer who did this, and all other car manufacturers refused to investigate because they have calculated before that this will be impossible. And the conversion of wind energy to methanol has a reduction of efficiency once more. And then you have a very good energy density of methanol. But you have to produce methanol from hydrogen, and you have efficiency losses. And afterwards, you should use the methanol, the direct methanol fuel cell. And this direct methanol fuel cell needs a lot of water additionally for the transport of methanol molecules through the cell. That means you need a lot of water on board of a car. And the efficiency is lower as a hydrogen fuel cell. That are the reasons why the whole automotive industry has stopped this development.
All right. For further questions, you can visit Dr. Johannes Töpler at his booth at E63.
Okay.
Once again, I thank you for this wonderful and interesting presentation. Okay. I'm sure you will have more questions at your booth.
Okay.
Big hands, please.
Thank you.
Congratulations, very good presentation. And
upcoming talk is unfortunately postponed to Thursday at 10:40. The topic is power management of fuel cells and electrolyzers in hybrid applications. It was held by Flexiva Automation and Robotic. Once again, it's postponed to Thursday at 10:40. Thursday, 10:40. We'll now have a short break and we'll continue at 1:40, that is in 10 minutes time, and we will continue with the topic addressing new technical safety challenges in developing alternative fuels infrastructure. And for that we'll hear the president of HiSafe in only 10 minutes time. Thank you.